lecture. So I welcome Dr. Rajiv Kumar Shakya sir for this session. Now over to Deepen.
Yeah. So as Gayatri ma'am already welcomed you, sir. So we heartily welcome you uh, to the day 5 of 2 week ATAL FDP on integration of WSN and IOT for agriculture. Uh, for the sake of the information for the participants, I just want to make you aware that Dr. Rajiv Kumar Sakya has did his BE and ME in electronics engineering from Sri GS Institute of Technology and Science, Indore. He did his PhD from Department of Electrical Engineering, IIT Kanpur. He is currently working in Edma Science and Technology University, Ethiopia. His research interest covers energy efficient node clustering, scheduling, and wireless communication protocols, WSN's MIMO OFDM, reinforcement learning in wireless communication, mainly focusing on MAC layer, routing layer, AI, and signal processing. For the participants, I just want to make you aware that Rajiv sir will be going to take both the sessions today. The first session will range from 7 to 7:50, and 10 minutes will be there for the questionnaire round. And the next session will be from 8 to 8:50, and the rest 10 minutes will be for the questionnaire round. Rajiv sir, you can take a 10 minutes break in between if you want. Over to you, Rajiv sir. Again, we
Thank
welcome
you,
you.
sir. Thank you very much for giving this opportunity. So now I can switch over to presentation.
Yes, sir. Yes, sir. Please. Please let me know that whether you are able to present or not.
Sir, click on present now, sir. There you go. Yes, sir.
Now my screen is visible to all?
Yes, sir, it is visible.
Visible, sir.
Okay, thank you very much for this ATAL FDP on integration of wireless and IoT for agriculture. So once again, I will thank to the JSS Academy of Technical Educations, Noida. So before start, we will have some outlines about wireless sensor network. What is the wireless sensor network?
Sir, sorry for disturbing. Maximize, sir.
Hello?
Sir,
please maximize your window, sir.
Not coming clearly?
Sir, full screen, full screen.
Make it full screen, sir, reverse. Full screen.
Okay.
Yes,
okay.
sir. Yes, sir. Now visible proper. Thank you, sir.
Yeah, so we will start with the introduction about WSN, then IoT, then how we can have a simulation scenario for these applications for research purpose. Then we will discuss about their modules, whatever modules available for NS3 in IoT and device-to-device communication. Then we will have some experiments on simulations. So we will start with the simple agriculture and IoT scenario. So this is an agriculture IoT scenario where sensor nodes are deployed in the agriculture field for measuring the temperature, water, heat, moisture, humidity, air, water level, and they are reporting to sync node. Then sync is going to report to the base station node. After base station node, through the internet connections, we can have a cloud, then it will reach to the users. So sensors here are generally reporting to base station. Base station will connect it to the internet on the IP network. Then through the IP networks, it is available for the users wherever they are. So this is scenario is generally most recommended scenario for field. So if we will see the wireless sensor networks research areas, so there is the power efficiency is a requirement. Also ideal listening is the another problem, so that duty cycle of nodes is also required. So we have a power aware MAC protocols, and also it is also supported to the IEEE 802.15.4 scenario, which is basically Li-Fi scenario. Now for the traffic, we can have a different type of the traffic in the sensor networks, multi-point to the point traffic, point to the multi-point traffic, and point to point traffic. So we can do the analysis using this scenario for research purpose. Now we can go to the IoT applications. So in short, we can have this type of layer architectures for IoT. We have physical layers, then link layers, network layers, transport layer. We have a UDP, TCP, and application layer can be the HTTP, or it can be another applications according to the devices you can connect. So 6 LoWaPAN will be basically also another module which will work on the link layer. Similarly, we can have another communication protocol, LoRaWAN. LoRaWAN will be another protocol. So these are protocols generally attached with the IoT applications. Then we can have information available to the users from the agriculture field. If you will see the protocol stack, so previously we have old protocol stacks. In this protocol stacks, we have a cloud, HTTP, TCP, IP layer, then normal MAC protocol. It is now converted to the new stack embedded with the wireless sensor networks. So new stacks will come up with these type of layers. We have a 6 LoWaPAN or maybe LoRaPAN, and we have a constraint application layer over UDP. So constraint application layer only responsible for getting the short message, not more data rate, not more overhead. So it is very much suitable for the sensors, actuators, and microcontrollers. It will give the information to the broader router nodes, then router will forward to the cloud. So here we can have a 10 second of bytes can be possible to transmit. So that's the beauty of IoT communications along with wireless sensor networks. We have millions of the data coming from the sensor devices, and without any acknowledgement, it is also possible. They have only request, send and receive token pass messaging protocol like thing. If you will think about that kind of integrations, how we can integrate them. So for simulation purpose, we can also simulate them in a simulator by kind of integration. So integration can be the stack based, can be topology based. So in a stack based, we have one server, and gateway is connected to the server. So gateway server will have IP connections, and gateway to the sensor nodes have own sensor protocol stack. So here two stacks, so that's why we call it as stack based. Another is a topology based. So topology based can be the tree type of topologies. So it will work on the 6 LoWaPAN protocols, generally in IEEE 802.15.4. Another is gateway solutions. Gateway solutions is applicable on the LoRaWAN. So LoRaWAN work on that scenario. Now we come up with the NS3 implementations, how we can simulate them. So we can install NS3 using Mercury. Also we can install by Tarball. Directly we can download this tdar.bz file. Then we extract that and run the program. Here we can clone by HG command. So all directory will be downloaded in your system. Then you can install by download.python program. release for installations. So we have many versions of NS3 is available. Many research communities are working on that. So till 2021, we have a 3.5. Now we have a 3.6 version. So installations, after installation, we have a first step to build by enabling examples and enable the test. So this enable examples, enable test will enable the feature of examples. So we can use their objects, their class files. So reusable is possible in NS3. This is the beauty of NS3. We can reuse the code and accordingly we can work on the scenario. And if you want to test the complete modules, those are installed in NS3. So by test.py, we can install all components. It takes 1 hour to check the all. So it will make the pass, track suit, test suit, test suit bearer, LT device, LT physical. So pass message will come on the command prompt. So it takes approximately 1.5 hours, 1 hour approximately to test the all modules. Those are installed in NS3. And we have a directories. So we have a directories is like that. So example directory is the directory where example codes are available, and SRC directory is the directory where our protocol module are implemented on C++ objectives and header files. So here all modules header and C++ files will be available. And another we have a binding with the help of Python. If we want to work on the Python directly, we can pass the data to Python and plot the data using Python program. Also possible we can pass the neural network module which are implemented in Python, then we can bind them in simulator to integrate the protocol according to the neural network algorithm. So that is also possible. So Python is also integrated in this. That is the another beauty of this simulator. So till now we can have a current modules implemented are these. These are the protocol range: AODB, DSDB, OLSR, click, OpenFlow, and energy model, mobility model, propagation models, which will gives the behavior of propagations, how much time is taken between packets reaching from sender to receiver, and what are the data rates. So that is the propagation. Energy is talking about the energies, how energy will be consumed, and that network is the core module is another core modules which will work on that, and application modules. And these are basically devices. We call it as network devices. If in your computer you can see there is a one network devices chip we need to install in desktop, then we can connect to the local area networks. So similarly we call it a net devices. So these are similarly net devices, because net devices are different for Wi-Fi, different for Zigbee, different for Bluetooth, different for LTE. So similarly we have a net device, LTE net device, Wi-Fi net device, CSMA, this is for local area network, LAN, Spectrum, this is for cognitive radio scenario we want to module. So that is the Spectrum. Then MES and WiMAX. So these many core modules, more code modules also added separately. More researchers are working. For example, we have a LoRaWAN. LoRaWAN is another separate module we can install in our NS3 separately. Another is new radio 5G communication modules. So that is also separate module we can install. So basically, if we think how NS3 is working, what is the implementation behind that? So implementation behind that is the API, basically helper APIs and container APIs. Two things. API is nothing but a classes or methods that will be called by scheduling some event time. So they can be scheduled for future 10 seconds, 10 minutes, 2 seconds, 5 seconds. So these are basically the class and methods. And we can also start another object which is attached with the class. So that's why container object and helper class generally are responsible for defining a different object for the different nodes. So helper is implemented using low level APIs. User can improve it in this API means we can make the another class for getting the status of the nodes, different status of the node. So that is also helper class is responsible for that. For connection between the node also helper class is responsible. So in NS3 we can have a configure by using WAF command, a WAF build. This is similar to the configure and Mac in the Linux. Linux we will use configure when we install any software, and we will use Mac for finally installing in Linux. So this is convert to the WAF and WAF build. So it is basically a time event simulators where discrete time will be jumped from event to event. C++ functions schedule the event to a specific time, and simulator run will get it all started, and simulator stop will be stop the simulation, and all event will be cancelled out at that time. So time is stored in the large integers in NS3. Special time class are provided to manipulate the time. Means we have a millisecond, nanosecond, all times classes are available, so we can convert according to that. Default time resolution is nanosecond, so all simulator will run in nanosecond duration time. If you want our time, then we can convert into normal time. So this type of object we can define time double t dot get second. So t dot get second is basically convert the time into the second if we want to have some value. So current development in NS3 we can have like this. So on this websites we can see the current development, what are the modules available for research and what are going to be available in future. So we have a sensor networks, especially for sensor networks we can have a 6LoWPAN. We have a LoRaWAN also separately available, 15.4 VNAT and wireless interfacing models also. So these many modules, LTE, newly added module are new radio, millimeter wave communication protocols. So these are newly added modules in the NS3. So
sir, does it has Bluetooth?
Yes.
Sir, does it has Bluetooth and Zigbee support as well?
Bluetooth and Zigbee support.
NS3.
Bluetooth Zigbee not available, but we can simulate same behavior in NS3. It is possible. So in the NS3, similarly in a mobile phone, we have an app store. So app store basically have all different application we can install. So similarly in NS3, we have a NS3 app store. So NS3 app store will give the different add-on modules we can add in the NS3. Routing, MAN, underwater acoustic network, LTE, public safety, reinforcement learning also coming, satellite networking, transport protocol, utility, and name data networking. So from you go to the site, you can see the releases and their update also on the given website. So this is another feature which is basically very much useful for future. So objective of NS3 is to migrate the NS3 to the real implementation. So we can have an emulator also. So simulator will become emulator. So that is the objective of NS3. So whatever implemented in the NS3 also it will work into the real-time scenario when we will implement on the hardware. Mobility model basically will gives the about node location positions and grid. So using that we can implement the any IoT scenario, or we can implement device to device scenario where traffic are flowing and road cars are going in the grid form. And so we have a grid module for creating grid, and random positions are according to the other devices which are connected. So we will use this mobility helper for defining this mobility model. Similarly, we have a for wireless sensor networks, we have energy models in NS3. So energy models will be added by using this include header file, Wi-Fi radio energy module header file, and energy module header file. So first we need to install energy source and device energy. Energy source device energy is be implemented with the help of basic energy source helper and basic energy source containers. So source when connected, then after that we can connect to the node with the help of device energy models, and Wi-Fi radio models will gives the consumption on the Wi-Fi scenario, how much away from the source to destination. So that will be also, and by using this command install, we can install the node to the all sensor network. So all nodes can become sensor networks. So separately, there is no wireless sensor network module in NS3, but same behavior we can implement using the Wi-Fi module. So simple structure of NS3 is like that. Similar is stack form structure. We have application, protocol stack, net devices. Net devices is similar to the interfacing device in your computer, which is useful for connecting to the LAN. Then we have a channel. So channel is similar to the LAN. Then after that, it will attach to the receiver side, to the network device. So simple OSI layer is implemented, and these components are different objects, basically class objects. So these class objects basically will be called according to the schedule. So that's why scheduling is a property of this simulator. So defined structure will be unique in this NS3. So defined structure will be like that. Simulator will start from man, then we have a attribute values, then we have a command line argument, then we need to define topologies, node, channel, devices, mobility, then internet stack we need to attach to the node. Then IP addressing, we need to assign the IP to the nodes. Then routing, we need to assign to the node. Then we need to add the applications and the number of packet we need to send. Then after that, we need to configure tracing. So tracing is also come up add-on with the NS3. So using the tracing, we can get the status of the each information, each packet flow, which time it will flow, what are the collisions, what are the physical parameter. So these physical layer, MAC layer, and network cell, we can trace using this tracing. So tracing is basically broad in this NS3 as compared to the NS2. NS2 tracing is very limited. After that, we need to have run the simulations. So this is unique structure of NS3. So basically, for understanding point of view, our basic objective is to get the information. We run the simulation, but how we can get the informations from NS3? So we have a three type of tracing we can collect the data. So first collection will be high level tracing. So high level tracing is similar to the tar file. So it is available for existing available. We just enable the PCAP. So PCAP trace helper will be get the information of all nodes, what time they are sending, which packet is going, what is the time, what is the overhead, what is the bit size, everything will be stored into the one file. So that is the PCAP files and ASCII files. So ASCII file is similar to the tar file in NS3, NS2. In NS2, if anyone have experience, there is one trace file is related.tr. So this is similar to ASCII file. Another tracing method is mid-level method. We call it as mid-level. Means we trace source. So exiting trace source we need to add in our code. Then we need to attach to the sync node. Custom sync node when we need to define some function which will call the variable of trace source. So that is then we need to attach to the sync. So this is basically mid-level methods. Another is high low level method is if you are expert in the C++, you can make the own C class, which will get the information of all node and store in a one file. So that is low level tracing. So if this is another methods, we can define own class, and own class will get the informations, collect the data from the scenario. So high level tracings is like that. For example, we will run this code, so it will generate the 4 files, pcap file. So pcap file basically is the network analyzer files we can see into the Wireshark. So Wireshark network analyzer basically is used for collecting, for understanding their patterns. So we have a time, source, destination, process ID information. So that information is all available into these pcap files. And many pcap files will be generated. And this number indicate the node to node, 0 node to 0 node, 1 node to 0 node. So 0 to 1 node pcap file, 0 to 1 node pcap file, and 1 to 1 node pcap file. So all link information, it is stored into the pcap files. Another is the mid-level tracing. As I told you, mid-level tracing basically is we can attach the trace source. So attached trace source will be like of similar things. So this is the make call, we call it as make callback function. So this callback function we need to attach if we want to get information about MAC transmission. This is the MAC TC is the existing trace variable which is available in NS3. So we can find out usually into the documentation library of NS3. So we can attach with this function devtx, and new function we need to define void devtx trace. So this function will be called by this trace. So when this will call, then in this function we can define what is the transmission address or what is the address of a transmission. It will, this function will pass, this trace will pass to the address value to this function and print on the command prompt. So this is a standout, so we can get the information on the command prompt according to the MAC transmission address. So this method is most popular. So custom connect to the track sync to the track sync trace source, and we can compute throughput, last packet and last packet timestamp and total byte receives. So we can connect the byte trace source, then we can get total byte. So for this finding trace source is another problem. So we can find the trace source in the Doxygen. For example, here in NS3 packet sync, we want to find out for calculation or through to. So in the Doxygen, we can find out like this type of object trace source. So this trace source we can attach with our node. So from this trace source we can get Rx variable. So Rx variable will give the packet is received or not. So packet received or not. So for throughput calculations, we can identify how many packet will be received and how many packet will be the. So this label tracing will be like this. We have an object sync trace source, or we will attach callback to the trace source. So that's why we call it as callback. Also, it is written in the form of make callback. So make callback, we can see in the examples, then we can reuse from the examples also. So this is another examples how we can find out the existing callback signature. So you can type in the command prompt by this execute graph call sync. So it will gives the many options where this callback signature is available. So we can reuse that code in our code. So that is another beauty in NS3. We can reuse the code and use the same callback functions in our code for our purpose. So this is, we can use this callback for packet syncs, and callback function will be trace syncs. And if you, then we need to, in the sync trace syncs, then we need to define these functions, which will get that time and store the previous time. So 2 times it will store last transmission time and first transmission time. So according to that, we can calculate the delay. So another low level tracing that is known as I told you, in the low level tracing, we need to define a class. For example, this I will show you this complete file. In this, we have a node status class. Node status class will calculate logs the packet drop events and store into the file. So many CSV files will be generated, and we can use GNU plot. So this type of CSV files we can have by using this class node status. Then we can use this CSV file for plotting directly using the GNU plot. So that is the another method of low level tracing. Now for wireless sensor networks, how we can simulate this? So we can simulate the throughput. So I will now switch over to the command prompt. So this is basically my directory. So all are looking this. So as I told you, NS3 is very large. So you can install separate module in NS3. So you can see here, this is LET modules you can install separately. Another is millimeter wave and NR new radio and NS3. So separate module you can have module install. So LS3 you can see this is LTE module. All LTE example can be here. So this is LTE module. Then new radio is for 5G communications. So new radio you can see that this is new radio modules. Now next is millimeter wave communications. If we need to have a short distance, then we can have this type of millimeter module will be added into the simulator. If you will run simulator after successful, these many simulator will coming and new simulator will be added with millimeter wave. Similarly, we can have 6 low pan another modules. So which is successfully installed, you can see build module build. Module not build will be those modules are not installed in your computer. So these listed will be available. So like that you can see. Then we have a NS3. So here we will do the experiment today. Today we will learn about NS3. So this is NS3 directory and this is netnm folder. So this netnm folder will be useful for plotting all node into the graphical form. So how node are moving, what packet is going. So graphical animations type of things can be possible with the help of netnm. And this is the NS3 folder where all modules are implemented. So these are the all modules we can see here. So Scratch is generally a common folder which will be used for running the default C++ file which you want to run at the current time. So here we need to paste our scenario and we need to run the simulator. Then it will run all your file which are available in the Scratch. So Scratch is basically a folder, common folder. Another is we can add folder in the contrib. So contrib folder is another folder. If you have a new modules, you have a new experiment, you can include into the contrib. So contrib is another option. So here you can see LoRaWAN. So here I have included the LoRaWAN modules. So this is separate module available for simulating the LoRa network scenario. So you can include into the contrib folders different modules. It is also possible. So we will start with the simple example. So beauty of NS3 is just we will start this simple simulator. Sample simulator will give you the feeling of behavior, how NS3 will work. So this is basically small code. So this small code will helpful how the schedule will be events. So here all events are scheduled according to different times. So we need to define the class as a C++ objective structure. So class is defined by my model. Then we need to define one function start. then private function will be defined handle event. So this is basically definition of the class. It is generally included into the header file, but here we are including same file. So handle, this object is start. Start function is implemented, and is scheduler simulator schedule second, and this function will indicate that this event will be scheduled after 10 seconds, because this time is basically future time, not the current time. Current time will be the stand simulator on now. So this command will schedule the event for after 10 seconds. Similarly, we have another module with the handle events. So handle events means call the another handle, and this is the initialization of the functions. So after initialization, another function also we have initialized, simple example functions. So example function basically have a input object to start. Start object, it is having input. So this function will call, it will start the object model. So my model I have defined here, so it will start this function. So this will start this function, then this function will schedule the another event for the 10 second future for handle event. Then handle event will call after 10 seconds. So this function will be called after 10 seconds. So here you can see one function we will call, that function schedule the another event 10 seconds. After 10 seconds, this function will call. So that is basically happening in the NS3. So according to time event will be scheduled. Then is start of the simulator will be from the int main. So main function will be the start of the simulator. So in the main is the initial positions, initial point where the simulator will start to run. So here we have defined the model, my model. Then we have defined the variable function, random variable functions. So random variable function will be v. So random variable function will be calculate the value between 10 to 20. So we have one random value 10 to 20 will become, that will be stored into the v. Then after that we will schedule the simulator at the 10 seconds, and it will, after 10 seconds it will call this function. Similarly, here we will schedule another event which will be according to the time we are getting from this random variable 10 to 20. And then we can cancel the simulator and we can run the simulation. Run the simulation, destroy the simulation. Now we can see here, we can see the behavior in NS3. So for that we will go to command prompt. So open into the command prompt. So this command prompt incoming. Now we will run this command using this option. So waf command, we will use the waf to run this code. So here we will use waf to run the code. So we paste this and for running this program. So now you can see here, it will compiling the all files in the Scratch. Now build is finished, build is successful. Now you can see this is calling the example function, random function. So random function receive at a time 10 seconds. So as I told you, in the main at a time 10 seconds, this event is scheduled and it will call these functions, and random event function will be called at 18 seconds. So 18 seconds is the time which is calculated by this random variable, uniform random variable. So uniform random variable will be calculating the time randomly. Then it will be called, then random function, then member function will be called at 20. So as I told you here, it is start will schedule another event of future 10 seconds. So 10 seconds is the current time, next 10 seconds will be the future time. So we have a 20. So that's why this 20 second is coming. So 20 second is a future time which will scheduled. So currently we are scheduling future event. So that is things. Now we can change here something. So what will be thing happen here? I will change the random variable 30. And here I will change the random variable 9. So it will calculate the random value between 9 to 30. Then this random function will be different. This event occurring time will be different. So we will do the same things. We will run the simulator. So now you can see here, random event time is 20 second. So you can see here difference between this and this. Events are, this is the event is coming late. In this event is coming first. After 10 seconds, it is coming. So this is the basically a basic theme of an S3 simulator, in which way it is working. So now we will do the another energy consumptions, and this, so this experiment we want to calculate. So we will simulate this example for simple mobility scenario. So this is the wireless sensor network simple mobilities. So here we have 5 sensor nodes. One mover node will be the sync node. So scenario will be like this. Sensor nodes are in the grid form and one node is mobile nodes. So here we have implemented the wireless sensor network scenario by mobile sync node and fixed sensor nodes. So for that, first we need to include all libraries. So these are the all libraries: internet module, network module, core module, OSR or DSR. Without that, it will give us the error, because from these modules we will call that object, we will add that object. So this is the option. In NetAnim module, if you want to see the graph in animator form, then you can include this. So first we will see the main function. So main function will be here. So main function is the starting point of the simulator. So main function, we are defining maximum byte, we are defining number of bottom nodes, what will be spacing between nodes and height and bottom row. Then we calculate the packet size. We have given the time. So this is all variables for calculations. Then after that we can use the command. So this is for giving the command through from the terminal. So we can directly use this function variables for giving from the terminal. Then we can have a simple steps. First we need to define nodes. So node container. Then we need to define Wi-Fi channel. For Wi-Fi channels, we need to define Wi-Fi helper, then channels. So Wi-Fi helper and Wi-Fi channel will be, we will use channel helper. So these objects will be, we will add. After adding this, we need to give them propagation time and delay according to them. Then we need to attach channel to the Wi-Fi physical layer. So Wi-Fi helper will be the Wi-Fi physical layer, and channel we need to attach by this command. So this command is attaching to channel and Wi-Fi. So after that, we have attached Wi-Fi channel. Then we need to define MAC layer using MAC helper. So MAC helper, simple ad hoc MAC protocol will be used. So prototype is protocol. Then Wi-Fi physical layer, channel and MAC we need to attach to the node. So this is the command. So all complete, we call it as network device container. So network device container including the physical layer, MAC layer and channel layers. Then after that we will install into the mover also, means sync node. So same things separately we have used this command for adding to the sync node also. So this is for fixed position node, sensor nodes. This is for sync node. So after that we can give the positions. So this is a mobility helper will be used for giving the position. So here we are giving into the grid form fixed node. So for fixed node, we will use the position allocation and will gives the x value, y value. So x value, y value is given here. After that, we will we will get the positions and we will give the velocities. So velocity is given by velocity mobility model. So velocity mobility model will be used here. Then we have our routing protocol. So here we are giving three type of routing where we can use OADB, OSLR, DSDB. So here we are using AODB. List routing dot add. So this is a command basically only adding the AODB. So OSLR, DSDB is not used here. After that, we need to store network stack. So network stack will be similar. We need to call network helper. Then we need to install to the fixed node and sensor nodes. Then we need to have a next step is IP configuration. So IP configuration is just by using IP address, IP4 address helper. So this is step. After that, we need to attach the source node sync node. So this is a step basically attaching the sync address is attached to the mover node, sync node, and UDP receiver is attached to the all nodes. So this is steps for defining the time, stop time, start time, and packet size, interval. We can also define how many packets we need to send, what are the interval between packets. Then we need to attach with the lower left. So lower left node we can attach. So here I am using two steps. Here is the only lower left step we can attach. And here we can attach sync node, source node to the all nodes. So this is the source node, UDP send. So we are attaching UDP to all nodes. So this is all node will send the data to the sync node, or this is one send, only lower left node will send data to the sync node. So accordingly, we can define the scenario. Then after that, we need to attach the trace. So here we are using only ASCII trace for getting stored the file into trace file. So one trace file will be stored by .tr. And this is for animations. Animation file will be .xml file, which will be called by the name animators. So we need to define that. Then we need to attach to the all nodes. Then here is the, if you want to write something, we need to give the name to the sensor. All nodes you need to give the name sensor. You want to give the sync node. So sync node we have only given to the mover node, and sensor node are all fixed position node. So after that we need to run the simulator, destroy the simulators, and at the step last we can count the number of packet received and number of packet by calling the UADP receive applications. So this is a simple example for simple wireless simulator. So we will run this code. Now we will check, and we will check on the simulator, and we will check on the animator. So this command we will use because this is in the scratch folder. So we can call this file and run into this terminal. So after this successful build, we can see here number of packet received will be 492. Lost packet will be 0, and packet actually lost will be 158. So more packet will be sent. So here I am calling this user helper else. So user helper else means, if you will see here, user helper else will be this option. So this is all nodes will sending packets. Fixed node sending packet. Here only lower left node will be sending. So I am running this. So all node will running the packet. So there is a huge number of packet will be dropped, and only received is 492. Now we want to, it will generate the one animator file, as here you can see. This file is generated for the animator. So we will see this file. So for that, we will see, we go to the folder and we run this name and net anim simulators. So we can open on the terminal and here we will start net anim. So net anim we will start, then this window is pop up. So this is the net anim scenario. So net anim scenario, then we can open that file by dragging. So we can use drag drop feature. This file is generated by our simulator. Then we can open that. So we can see here, these are sensor fixed node. This is the sync node. I've given name also, so name also coming. We can increase the size here. So we can increase size by option this. And by this button, we can run the simulator. So you can see here, it will show the complete behavior of how packet is going on. So this circle indicates the transmission between two entities, two nodes. So we can increase the speed here. So when we increase the speed here, so we can see node is moved, sync is moving, and all nodes are sending packet to each other and sync reaching to the sync. So as sync node moving, the packet will be flowing in these directions to the multi-hop. So sync moving in this direction, so they are following multi-hop scenario. If sync is near, then it is single hop scenario. So both scenario is simulated in this example. So this is one of the example for calculation of behavior in the TR file. So TR files also we have .res files. So .res files we can see here in NS3 folder. So this is the res files we got. So this is the name file, then trace file will be, we have a pcap we have enabled, so we have this files, pcap files we also got from this example. So this is simple wireless sensor networks examples. So we can calculate these things. Another, we can try energy models. So energy models is another example. So in this energy models, we can run this training energy model examples. So it will calculate the energy for current remaining times and total energy consumption by the radio for different time durations, and total energy consumed by the radio in so this time of according to time slots we will get the results by these simulators. Another example, similarly we have this train Wi-Fi sleeps.cc. So this example basically is a calculation of energy depletions. When energy is drained by the nodes, then automatically sensor, that corresponding sensor will go into the sleep mode. So it will activate the callback function, callback trace functions, and put the node into the sleep status. So it will generate the three files. Three files will be energy.log, energy 1, and state 1, state 0. So energy will give the remaining energy of node of for node 1, for node 0. So every nodes have a different energy status. So this can be stored into this file. So we will check this example. So this example is this energy training energy model example. So in this example, energy model is used. So we start from the main. So in the main, steps are same. First, we need to define packet. We need to define node container. Then we need to define channel. Then we need to define Wi-Fi MAC. Then mobility model. Then this we need to add. So additional things in this example is the energy source helper. So energy model is used, energy source helper and Wi-Fi radio energy model helper. And both are attached with the device and source. So the network device is the network device attached, and source is the energy helper and source helper. So that are installed by this command. So this command is basically installing to the device. Device is the network device. This one is the network device. So network device means it is having physical layer, MAC layer, and node attached. So this we need to define. Then we need to attach to the trace. So this trace after definition we need to attach to the node. So here all sources are connected to the node. So by this command. So here we are source.get0 means first node is attached to the source and callback function is attached. So here this remaining energy function is tracing callback is used here. Low mid level tracing method is used. So this remaining function is the function which is called by the energy. So here we can see. So this is the function, remaining energy function. So remaining energy function basically will be called by energy source and where we can get the variable remaining energy. So remaining energy and variable we get, then we can print on the terminal. So this is the terminal print command. So this function will be called when by every time durations, interval times, and status will be updated on the terminal. So this function will be updated every times. So this is for remaining energy. Total energy, similarly, we can attach the total energy trace file. So this function is total energy trace. So total energy consumed by the node. So this is also called total energy called by the another trace source. So this is trace source which is we attached basic radio model pointer and make callback total energy. So main callback total energy, this function is basically called by the trace every time when consumption is taken place. So durations will be given into the schedule event time. So we can run this example. So we will run this example. So command will be like this. Training energy model. So this command we copy on the terminal. So now you can see we can have this type of output. Current total consumed energy. So total energy function will be scheduled by the event, then printed on the terminal. Remaining energy, then printed on the terminals. So similarly, we can get. So this is the example for giving how we can calculate the remaining energy and store into the file. So if you want to store it to the file, we can define the function and open the file into that function and store into the file that function. So we can store this command prompt informations. So that example also we can run by this example, second example. So second example is training sleep, Wi-Fi sleep. So it will gives these many output. So we can set these many output. Initial energy we can set voltage, we can set durations, we can set how many packet size, data rate, and transmission power level, radio level, ideal power level, in ampere. So these many parameter we can give to this single file. So first simply we run this example. So it will generate the three files, four files. One is status, one for energy. So this is example basically storing the file into a txt file. We will store all data of energy. So now build is successful. So we can go to the folder. So here we can go in a scratch. Then here we need to open this file. So here we can see in this file we have given this file. We have defined this function for each node, and we have created this folder, and inside that folder we are storing energy of each node with the extension txt. So txt will be the extension or store into the folder result WSN. So we need to create here result WSN folder. So result WSN folder we can create here. Folder is already there. So it will give the output of like this: energy 01.txt, energy, this is for node 1, node 0 and node 1. So if we will open this file, these status will coming over different times. So this is the time, or this is the status, remaining energy. So all remaining energy information you can get for the node 1. So this node 1 will gives the all information energy. So here we have given the file result WN folder, and this energy. So it is storing into the folder. So this is example for we store the result of conjunction of all nodes into the folders. Now we come to another example. Another example is for IoT simulator. So IoT simulations, we need to, we have these many IP module are implemented in NS3, LP, LRWPAN, LoRaWAN, 6 LoRaWAN, and IPv6. So these modules are basically available for simulation. So we have two type of communications. If you want to direct communications, we can use LoRaWAN, star-like topology, full long and short range. So this option can be NB-IoT and LoRaWAN. So in the simulator, we have a LoRaWAN module is implemented. For multi-hop communication, mesh topologies, we can use LRWPAN. So it is basically nothing but a standard IP.254 for implementation. So in NS3, basically module architecture will be is like that. We have a physical MAC layer, and on MAC layer CSMA protocol implementation is done with the sleep backup mode, and energy model also available, radio energy model and energy source model for connecting, for getting the power consumption of. So we can try these examples for LRWPAN simulation. These are available in the example folder. Then next is the LoRaWAN. So LoRaWAN is basically long range communication protocols. As more previous, we can install by this GitHub websites by using git command, or we can install, we can get the any queries from this link. So this is basically many features operating on the low power, low connectivity cost, provide easy deployment, quick setups, and high directional. So next session we will understand about this LoRa one. So I can stop here. Any questions? Anyone can ask me.
Hello, sir.
Yes.
Yes, sir.
Yes. Hello, sir. Can you tell whether leech protocol is there is in NS3? Leech protocol.
Leech protocol, ma'am, not available in NS3. But we
Not
can
available in
simulate the
NS3.
scenario. Same behavior we can simulate. We can group the nodes,
Okay.
clusters we can make, but same to same is not available.
Okay. Okay. And sir, for directly for getting the throughput, in the LoRaWAN, in the next section, I think you will discuss the same.
Yeah,
So,
next section I will
that was-
discuss with the implementation via multiple gateways.
Okay.
Simulation also scenario I will explain how the data tracing is done, how the packet we can
Okay.
calculate. So basically, if you can give me time, I can show you another example for calculating everything in a single file using flow monitor. Flow monitor module is more important, more useful. It will work on the IP layer. So IP layer, whatever packet
Yes.
status it is having, it can calculate. So we can discuss
Sir,
if
that please tell.
next session. Now
Yes,
I
in
can
next
tell
session.
you.
Yes.
Next session we can discuss this. So flow monitor is more popular for collecting the all information, packet drop, end-to-end delay, latency, everything.
And sir, is there any TR file? You told that TR file is there, but PCAP file you told after that.
PCAP file is for PCAP helper. TR file is for ASCII helper. So both are separate. We need to enable them. Then they will come.
Okay, sir. Thank you.
Good evening, sir. Sir, I have a question.
Yes.
Sir, there are a lot of network simulator available, NS2, NS3, OMNET, and etc. So which one is best to use? For example, if we have to do the energy consumption model, we have to minimize the energy and maximum throughput. So which simulator is best? Because there are a lot of simulator and there is a confusion amongst all.
Actually, honestly, speaking, if you want to work on open source, then NS3 is well supported because more users are working on that. If any error you are getting, errors you are not getting output, you can get the information from the Google group. There is a NS3 Google group. So this is the another advantage for NS3. There is a more people are working. You can reuse the code. You can get the information. You can rectify your bugs, your errors, everything. If you want to work on the licensed version, then QANET is the another simulator for energy consumption. That is very easy, but it is licensed version. I used one time. It is simple actually. So,
Sir,
but
sir,
Qualnet is costly, sir.
yes.
So can we use multi-hop transmission in NS3 multi-hop transmission, multi-hop?
In this NS3, you can see NS3 basically is giving the actual behavior. Actual behavior in the sense when packet are having antenna, there is a device, antenna will be there. So antenna transmit the packet to the receiver, receiving antenna. So packet will reach according to the SNR. Signal to noise ratio will be proper to receive reception of the correct packet. So in this scenario, we have a DB option. We can set the transmission range according to 12 dB, 15 dB. So that is the basically NCNR value, actual behavior of particular scenario. So due to that measurement, we can simulate the different scenario, or we can simulate according to the position of the node by using mobility model. So maximum here we can have a 250 meter range. So accordingly we can make our scenario and make the move multi-op scenario. So two
Thank,
feature are there in NS3.
thank you, sir.
Any other question? Okay, sir. You can have a 5 minutes break, sir.
Yeah, we can have no problem. I
Ah.
can start and anything. We can have break, no matter.
Means just for you only because you are speaking continuously from more than 1 hour. So that means you can
Here
have a rest.
only data. I have no problem.
Okay, if you don't have any problem, then you can go with the session, sir.
Yeah, we can go with. Actually, I can explain the flow monitor example.
Yes, sir.
Okay.
Then go, sir.
So
Go with it. Sir.
flow monitor example. So we can go to this. So here we can have a flow monitor example. So in this example, basically we are using flow monitor. So flow monitor is just little steps we have. So we start from INIT man. Then this is normal definition of the nodes. Then on-off application we need to attach CBR transmission for packet transmissions. So packet size and data rate. Then we have we have connect the Wi-Fi, then we have defined MAC, then we have attached to the device, so net device, then we have used the routing, then IP assignment, then mobility for topology creations, then CBR packet generation steps. So CBR generation start and CBR reception stop. After that, these two lines we need to use for whole monitor helper object we will call, and we define the object flowmon. So flowmon object is basically flow monitor object. Then we will attach by this install all command. So install all command is basically attaching to all nodes. So flow monitor is attached. So it is having pointer to monitor. So monitor pointer we got here. So for getting result, we will use this monitor pointer. So after the simulation start, here PCAP file we have enabled, then animation file we have enabled, and the simulator run. Simulator is started. So after simulation is started, monitor file object will be calling here and check the lost packet. So lost packet function of flow monitor object will be called, and using that we can calculate transmission reception throughput, end-to-end delay, and packet delivery ratio. So this function, this object we call, then here we are using flow monitor object function variables monitor, and we are calling according to the different flows. So flows are identify. Flows is nothing but data transmission between sender to receiver, how many path it is making. Flow is nothing but the path of packet transmissions. And using standout command, we can print on that command prompt. So these lines and before this lines and before 3 lines, these 2 lines are used in the simulator for adding the flow monitor feature in NS3. So now we can run this file. So we can run by this command our file in the scratch. Then we can run by using so on terminal we can get build finished successfully. it takes time actually, because it depends on the number of flow, means how many sensor node, how many sender node, how many receiver node. So sender node, receiver node should be different, then it will take time.
Sir, from where
Now
we'll
we can
get the
see,
code for
we can see now, this is output. So we get the output now, flow 1, between node this one to node 2, number of byte transmitted will be this much, receive byte is 0, throughput 0, delay 0, percent delivery 0. In flow 2, from between to this, we have a transmission byte, receive byte, throughput will be 0.01 something, end-to-end delay will be 0.07 seconds something, and packet delivery ratio 1%. Similarly, we can get for flow 3, so 4% delivery ratio, and flow 4 and flow 5. So number of flow will increase, it takes time actually. Total flow will be 10 flows. We have a 10 nodes, so 10 flows will be there. So this output we can get on the terminal with the help of a flow monitor. So in this example, we can see here, total nodes we are getting 10, and flow we have a 10 flows. If you will see sender application and receiver application, so you can see sender application will be this CBR generations, node J 124, this is the sender and start time, and this is receiver. So sync and source will be 5. So we have a total 5 flows for all nodes. So this is example for calculation of the all detail in using the flow monitor. So in this, any question?
Sir, from where we'll get this code?
What code?
Sir,
Ma'am, this
whatever
code is
this you have
easily
told.
available. You can search on the Google group. NS3 Google group will be there. They will
Okay.
discuss. They will share their code. They will share how we can add these modules, how we can add flow monitors. So same. This I got from the one NS3 group. NS3 group some person has used actually. So I will share you if anyone want this.
Okay.
So this example is for. So we have discussed these examples, and sleep mode we have discussed. Flow monitor. Now we come to the LoRaWAN simulation. So LoRaWAN simulation, how we can do? So we start with the second session. So second session we have on LoRaWAN. So in this session, we will discuss a little bit about LoRa, how is it to work, what is the research, what are the research challenges, and how and LoRa module in NS3, performance parameters, what are the performance parameters we can have, and how we can comparative candidate. So we will discuss shortly. So basically, I will skip this IoT. IoT is more popular and more advancing. That's why LoRaWAN is mostly used in many countries. So many countries already using this. So three type of modules are available for IoT: device to device communication, device to cloud communication, and device to gateway communication. So device to gateway communication is based on the LoRaWAN architecture. So this is an example of device to device communications. Simple sensor is connected through your mobile phone. So you can get the information on your phone from the device. So that is a device to device communication. And device to cloud communication, information is going to the cloud. And device to gateway communication, there is a one gateway in between devices which will get the all information from the gateway from devices and transmit to the application server. And another is backend data sharing communication module, where different application also can communicate on the IP and on JSON or HTTP. So low power wide area networks is now going to be more popular. Many companies are using because it is having more advantage than the traditional cellular technologies, because these all technologies are high range communication technologies. Or another feature of another example of low power network is LoRaWAN. Any other example can be NB-IoT, New Radio IoT architecture, and Sigfox architectures. These are the other communication architecture for devices. So today we will discuss on LoRaWAN. So it will basically have a CSS technique, physical layer architectures, and MAC layers also simpler. And module will be CSS, and MAC have a three classes: class A, class B, class C. So I will not go to the detail. I will discuss with the module implementation. So in the NS3, it is module implemented in this form: sensors, gateway, and server. So three modules are separately implemented and linked with the another channel. Here we have a LoRa channel, and here we have an IP network channel. And every modules have a MAC applications, net device, physical layer. Similarly, it is having LoRa physical layer gateway, and it is having IP server, LoRaWAN's master gateway server. And it is operating on the basically a three bandwidth: 125, 250, 500. So three bandwidth also available in NS3. We can use them. And ATR, data rate control schemes, is also implemented. So this data rate control is basically for managing the data consumptions, battery life. So we can modify ADR for making the energy efficiency. Communication range can be 300 communication rate to 5 kbps for 125 kilohertz. And the structure of layer implemented are like this: physical layer, MAC layer, and application layer. So this is simple architectures of LoRaWAN like this. We have a gateways, LoRa devices, application server. So research challenges in this basically according to the quality of service. So quality of service is the matter of concern, because we have more devices, more LoRa modules, so consumption is more. So how we can optimize the energies, how we can optimize the transmission power of ED and devices or LoRa devices, we call it as ED. Another is quality of sustainability. Means every device have some battery, so it will also generate the waste. So how we can, this is another parameter we have given, is chemical waste generation from batteries. So that is known as the quality of sustainability. So QIS and QIS, two parameter basically are having trade-offs according to the different technologies. So we can optimize these parameters by increasing number of gateways, by increasing transmission power, by increasing cost, number of end devices, number of LoRa's. So we can do the simulation for that purpose. So similar behavior of actual scenario can be is implemented in the NS3. So it is available through the git command. So we can get from this link and we can add into our simulator. So LoRaWAN folder is created and all module will be stored in that. So by roughly we can see implementation of objective functions. So these many objective functions are implemented for LoRaWAN modules. These are the net devices. This is physical layer, LoRa physical layer. Then this is for network server layer, application server layer. So they are connected with the some parameters. Similarly, we have frequencies for different frequencies, LoRa MAC layer. So structure will be like in this fashion: network server, network device LoRa MAC module, gateway device LoRa physical module, LoRa channel, and end device LoRa physic, and LoRa MAC and periodic sender. So this architecture is implemented. So in the latest version of LoRa module, we can have a multi-gateway support. We can have a support for adaptive rate, or we have a support for interference modeling. Mean we can also model the interference between the modules, how many packets are lossing, what is the collisions. So this also we can module. We can also module another scenario that is known as building scenario. Means more buildings will be aware, and from the buildings there is some obstruction also there. So how the packet is transmitted, what are the throughput, what are the delay. So that is also known as the real scenario. So in the NS3 we can also module the building scenario, how much far is the gateway from the ground, what is the height of the antenna of the gateway, what is the height of the. So this scenario actually is important because these are the long range communication protocols. So distance also considering in terms of the buildings. So that is also we can simulate in this simulators. Performance parameters we have similar performance parameters some, but new parameter is included here. Some researcher has proposed waste total. So waste total is basically calculate produced chemical waste from battery to of end devices during operation time of the network. So this parameter is a new one. Another energy consumption is old, delay. We can calculate packet success rate. So today we will discuss two type of scenario: realistic model scenario, where use of the building is given in the area, and non-realistic scenario where no buildings. And we can have a gateway, one gateway, and others are in the circle. We have end devices, LoRa node, and 2 gateway, 3 gateway, 4 gateway. So similar behavior we can see in the simulator. So now, so I told you I've already installed this NS3 into contrib folder. So what is the contrib folder? This is the contrib folder. So this is LoRaWAN. So LoRaWAN module is installed in my contrib folder of NS3 3.32. So in this folder you can see this is basically README file, and these are all modules implemented which we have discussed: end device LoRa MAC, physical layer status, gateway LoRa MAC, gateway physical layer, gateway status, channel allocator. So these basically functions defined in these files is basically moduling the same behavior of LoRa architecture. And here we can see the example. Example we can find out here. So we have many examples. So we can find out the example ADR protocol and other comparison energy models LoRaWAN. So now we can start. So So I will make this, I will put everything in the stretch. So stretch so this is the basically simulations. So here we have a three study we will see today. Gateway 1. So here we have a script for gateway 1 script, 3 gateway and 7 gateway without building and not building. So we will see in the file. So this is basically LoRaWAN file. So this is a simple networks that use ADR algorithms to set up the spreading factor of devices in the network. So spreading factor so this is similar to the we have a header files for LoRa header files, LoRa physical layers, all. Another we have a point-to-point link for creating the link between gateway device and server. So we need to have point-to-point link, wireless link between, and there is an energy model, a LoRa energy model. So start program from main. So here we will define the devices. So total devices here we define 500, radius will be 750, channel model we are using, and we are using multiple channel fee things. So this is the arguments all. Then we will use the building scenario. So realistic channel model is basically giving the scenario of building. And after that we have a propagation channel model. Then we define the mobility model for end devices, mobility model for gateway devices. So two separate model, two mobility helper we will use 2 times for mobility for gateway and mobility for devices. After that, we will add the physical layer. So the physical layer helper will be used, then MAC layer helper. And then we create the gateways. So number of gateway will be created. So n gateway means here we are gateway, have one gateway. So this will be one parameter. After that, we gives the location. So 0050, this is the gateway will one location. Then we create the net device for gateway. So net device, this is function for creating the net device of gateway and install all layers, physical MAC and gateways. After that, we will create the end devices, LoRa node. So end devices, so similarly for node container object we will use for creating the node devices. So this is the node container objectives. Then we will install mobility on all node devices. After that, next step is to gives the node with certain height. So that is a function we can give by using mobility and get positions. Next is address allocations. So this step is defining the address allocation, generate address, LoRa device address generator. So this objective is used. And then create the net devices for end device. So gateways are connected with the end devices by this helper.install command. So helper.install is connecting to them. Next is handling the buildings. So handling buildings, we model also available in NS3. So we will use the x, y, height, delta x, delta y, and calculate the width, grid width according to these parameters, and attach to the node by using grid building allocator function. So grid builder allocator function basically gives the behavior of buildings according to the height, length, and their distance between nodes. So height, length, and distance between node. That is the uh, delta x, delta y. So this is the setting of attribute variables. After that, they are installed to the end devices and gate devices. So installing is nothing but attaching to the end devices and node devices, and get the printing of informations. We can print information to the file by using this function. So we create the one file and open the file, then store the all object into the file by this command, my file command. So here we are storing detail of buildings into the file. So after that we close the file, and next step is selecting the spread spectrum techniques. So this is attached to the channel and gateway. Then after that, next step will come the application layer. So we need to connect the application to the end devices. So application period will be 600, means one packet every 10 minutes it will be transmitted. Because we have a 500 node, so that period we can calculate. So according to that, then application attached to the end devices. So end devices is we can attach to the applications. Next step comes to the network server. Because LoRaWAN architecture have a node, end devices, gateway, and server. So this step is server. So node container server. Then we have only one server we created. Then install network application on the one server. So this function will give the non-server applications. Then after forwarding applications attached to the server gateway. So this gateway, so all packet is coming to the server by this forward helper. So gateway, anything gateway will get, it will pass to the server with the help of this function. After that, we will attach the energy model. So this step is attaching the energy model with the help of energy helper. And after attaching energy, we will store the information, install into the all devices, and we will get the energy of all nodes. So energy of all nodes we will get by attaching the source to each node. So this is node 1, node 2, node 3, all end devices we will attach to the source. So this command is saying, since we have a 500 end devices, so some devices we attach 1 to 30 and 148. So here basically sample, we have not attached source, energy source to all devices. Then next step is store the data into the file. So this steps is every energy, which energy source we attached, we store it into the file. So this file 0, file 1, file 2, this helper will be used for storing the file into result folder, and all different node file will be created for different node 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, and 148. So what those we have attached the source, we are storing the result of energy consumption, remaining energy into corresponding file. So that's why this labels is given. At 18 labels mean 18th node. This is 148 label mean 140th node. And it is calling the trace source. After that, we will start the simulator and track the packets. So this is the packet trackers for tracking the packets. Then we will we will store the all information of end devices into this file .date file. So .date file will gives the number of status of the node files and their power consumptions. Then we can start the simulator here. So a last step of this program is this stop the simulator, run the simulator, and destroy the simulation and print the trace output. So this is all about LoRa one gate example. So in this example, you can see we have created the gateway, node, server, and LoRa, and we have attached the energy, and now we can see here the result by running this code. So we will run this command waf run scratch one gateway. So as you can see, it will store the result into result folder. So here first we need to create the result folder. So we will create the result folder. So all data will be stored into this folder, because here we have given folder name result. If I forgot to, building.test file will be created, which will give the information of all building locations. And another is we are storing this results. So folder name should be the results, not the result. So we will change this folder name results, because if folder name cannot be same, data will not be saved into this folder. Now we can run the simulator, run this program. So on the terminal, so it is compiling some error is coming. I think we have switched to the LoRa module. Before we were on the Wi-Fi module, so there may be some error coming. Okay, for time being, I will show you the data. So we can have this type of
Hi, Alisha. This is Monica Malik, ma'am, from Electronics.
output. Gateway 1 output will be like this. So we have this type of folders. Battery level 1, level 0.txt, battery level 1.txt, battery level.txt. So this file is created by the simulator, which will be giving the time and their energy. So energy will be 1000 we have given. So 1000 energy will be displaying in this. So likewise, we have a 1 to 19, 30 and 148. So you can see here, we have given 1 to 19, 30 and 1930 and 148. So same files we are having. Another we have a file enddevice.dat file. So this file is basically for storing the information of end devices. So these are the informations we can get according to the XYZ. So we can plot on the.
You just send me your appointment letter.
So we can plot by using this command. So we can have this type of structure, location of end devices. So this is the location of end devices, XY locations. So we can create this graph using simple this command. Simple we can use.
That will do. That will do. No problem. Or maybe just a snapshot of that but first page.
Perl script file. So Perl script file will give the data.
Product manager. That will do. No problem at all. Okay. And I think this company is in Noida, right?
So likewise, we have a gateway 3. 3 gateway we can have this type of topologies. This is gateway 4.1, 2 gateway in this area, 3rd gateway in this area.
Okay.
So it is generated by the end devices second file. Similarly, we have this 4 gateway. So 1, 2, 3 and 4 gateway. So this is 4 gateway. And similarly, we can have a 7 gateways. So we can plot the result using our. So in this example, we can see we have a gateways and end devices. We can set these many parameters, uniform distant allocators, every across the circle, and payload and time durations, bandwidth 128 kilohertz, and we have this type of file is generated and devices, and this. So description about simulator will be number of node, payloads, interval time, path loss component, and transmission power of end node devices in dp, code rate and duration of the simulator. So we can have a result like this. Time simulators will be run like this, and we have a three files: end device files, battery level files, and screenshot of stored end device locations and battery level locations. And this is the basically different locations according to the different multiple sync, and we can have a result for like this according different scenario, energy consumptions for this node, and PSR, average delay, and chemical waste also we can calculate. So this is all about the LoRaWAN. So we discussed in this realistic, non-realistic scenario, and how we can calculate the quality of service optimization. So using this NST simulator, we can do the performance analysis for transmission power, spreading factor, for quality of service by optimizing the location of gateways. We can also use the machine learning algorithm to place the optimal location of the gateway so that the power consumptions and interference should be the optimal. So thank you all of you. This is all about the LoRaWAN. Any questions anyone can ask me?
Sir, sir, I am Ganesh here.
Yes.
I have one question, sir.
Okay.
Sir, actually, for how we can find the best suitable spreading factor for given ranges?
For
given range,
actually in
for example,
LoRaWAN
10
architectures
kilometer.
configurations, they are spreading factor also changes according to the transmission range. So it is defined for 7 level.
Yes.
Are defined it is in the NS3. So we can use that configurations.
Okay. Whether that option is there, sir, available in this?
Yes, spreading factor option parameter is there in NS3. Similar to the architecture implemented by this company. They have LoRa module configuration architecture. Similar behavior is given with different spreading factors. What will be the transmission power and what will be the distance of gateway to the end node devices. I forgot actually, but I remember this. There is just one table.
Okay, sir.
Yes.
Thank you, sir.
Yeah, namaskar, sir. This is Sonu.
Yes.
Sir, actually, if I will talk about the some biomedical sensors, means devices like ECG or EEG or PPG type of sensors. Suppose I have designed some program by using C++ on Arduino side, Arduino IDE. So, sir, how can I save some biomedical data into some CSV file or any other format so that I can implement that on Python IDE for machine learning application?
Actually, biomedical data is not my area.
No, sir.
You are
sir.
talking about implementation thing. Sorry for that.
No, sir.
Simulation part, biomedical data, I am not having any idea.
Sir, not only for biomedical. Actually, sir, I just want to know how can I save some any type of signal data into CSV or any other format of file, sir? Because I saw one format of I saw one code on Google, and I have implemented same thing on Arduino also, sir, but not getting exact response from that. Means I am unable to save that file in CSV. Any signal data, actually, sir, not only biomedical. Yes, sir.
Actually, I told you one idea. You can take some assumptions because biomedical signals are basically discrete signals, how we can measure them? Measurement parameter should be in terms of some signal strength, in terms of some SNR values. So that also helpful if you can use SNR for signals.
I think Sonu Kumar, hello,
Yes,
Sonu sir.
yes, ma'am.
Yeah, I want to answer this question. Actually, you are just, I think what you want to ask is that you are attaching some sensors to Arduino, and from that Arduino board, you are transferring the data to, and you want to get the data in the CSV file. Am I right?
Yes, ma'am. Yes, ma'am.
Okay, so there is what you can do. You can use Node MCU, and from the Node MCU, you can directly take the data through Wi-Fi on the cloud, and in the cloud server, you can have that file, and you can draw the, like, you can have different graphs also, maybe available on the cloud. So directly you will get the data saved there.
Actually,
So
ma'am, that is
some
possible.
experiments are also given.
Yes, ma'am.
Yes, yes,
But
that
cloud
is
data,
possible.
yeah, I think, ma'am, cloud data can be possible for one or two type of electrodes. But once I will put some 32 electrodes on some scalp, or more than that, that much of electrodes, then I think it is giving some problem by using cloud. Some interrupt type data interrupt will be generated. That's why I'm having some problem. I thought that okay, no problem, sir. Thank you so
Okay,
much.
that depends upon, like, you can, yeah, you
Uh,
can program your system like that, and scheduling may be done so that one by one your data may be saved. Like you are using 32 sensors, and you want to get that those data actually all together. So
yes,
one by one you can have the task, and you can initiate the task one by one in round robin scheduling, and you can get the data.
yeah, definitely, ma'am. I will try. Okay, ma'am. Thank you so much. Thank you, sir.
Okay. Sir, I want to ask one question. Sir, in the LoRaWAN, you have talked about the simulation environment. So, sir, how, let us suppose we are using, you have told that we will use one gateway, two gateway, four gateways. So, sir, in if we are using one gateway with, let us suppose, 10 LoRaWAN nodes, so that one gateway is having the range of around 10 kilometers. Am I right, sir?
Yes, yes.
One LoRa gateway is having the range around. So, sir, if we are using more than one gateway, like two gateways, four gateways, so it is unnecessary. It will increase our cost. And how we can measure the throughput in terms of the we are increasing the number of gateways, and then we are measuring the throughput.
Ma'am, in LoRaWAN, basically throughput is not important criteria for measuring the data.
Yes.
Important criteria is life, basically, because now millions of devices available, so they are connected with the gateways. So concern is about because they are low data rate devices, low data rate devices. So range also wrong. So power consumption is another concept. Another concept is basically of placement of the gateways. They are the trade-off between the transmission power and number of gateways and end node devices for particular applications. So as per literature, actually, these are the challenges.
Sir, I request
Sir,
please.
but why increasing the gateways?
Actually, simple application, we can use one gateway and LoRa.
Yes, sir.
But you can see previous
Okay.
session, last yesterday's session, they told one gateway is more costly, 1 lakh something. For a people goes for high range. So only one gateway I am purchasing for 1 lakh. In a space of 1 lakh, I can use 5 gateway for cheap cost. That is also possible, I think. So cost also minimized.
Rajesh sir, if
So now
possible, can you share
performance.
those codes, sir?
Yes.
If possible, please share those codes, sir. We will try once.
Yeah, of course. I will share you. No matter. I will give to the this FDP coordinators. Then they will.
Okay,
You
sir.
can get them, I think.
Thank you, sir. Thank you.
Sir, please give
Yeah,
us the
no
links. We
matter.
will share with the we will share with the participants also, and those
Yeah, yeah.
who require these codes, we will give. Okay, sir.
Any more questions from any of the participants? Okay. So I guess no more questions, sir. So from the organizing committee, I convey heartfelt thanks uh, that you spared time for us from your busy schedule and delivered a very deep insights from the practical aspect about the topic. Hope the participants would have been benefited a lot and many queries have been answered from your side. So thanks a lot once again, sir.
Thank
I'll
you, sir.
be
Thank you.
so hope the slide is visible to you. It's a token of gratitude from our side,
Thank you, sir.
virtual
Thank you very
memento,
much.
Thank you, sir.
and for delivering two sessions, the
Thank you,
two
sir. Thank you very much.
certificates are there.
Thank you, sir.
Thank you.
Sir,
Have
can
a
we
nice
have
day.
one photograph, sir? Sir, switch on your cameras. Those participants who can switch on, we will take one photograph. Okay, so I am get ready, please. I have clicked the photo. Thank you so much,
Did
and
we
thank
miss
you,
sir?
Rajiv sir. Yes, sir. Thank you, Rajiv sir, from my
Thank you.
side.
Thank you
Very,
very much,
very,
Thank you,
ma'am.
I'm
Rajiv
very
sir.
thankful.
Thank you,
Thank you,
sir.
sir.
Thank you very
Considered
much.
our
Thank you.
request, sir. Okay, very nice
Thank you.
session, sir.
Thank
Thank
you,
you,
sir.
sir.
Thank
Have
you,
a
sir.
nice
Thank
good night.
Good night.
Good night, sir.
Good night.